Welcome to the pre-recording of lecture 31 of MCS 481 on computational geometry. So this is our last lecture before the midterm. So in the next lecture we start to review. It's also the lecture where we're going to close chapter 10 in our textbook. So this is really a milestone. It's a lecture on geometrical data structures for solving windowing queries. So we introduced interval trees, priority search trees in the previous lecture, and today we're going to talk about segment trees. So what's the problem now? Um, so we want to zoom in. We have a map. So here is the picture at the left. We have line segments, and we want to select all these segments that are lying in a window. It could be an actual window if you are building a flight simulator. So the landscape that is displayed below, you kind of see this sliding by as your plane flies over it. So this is not an applied course, so we are not going to go there, but just to motivate, we are looking at the mathematical perspective and towards understanding how this can be solved very efficiently. So this is our problem. In the previous lecture, we actually wiped out all the segments and looked at the dots. In the lecture before that, we were assuming that all the line segments were horizontal, and we were then considering um, the stabbing queries for which the interval trees were very well suited. So in this lecture, we consider the segments. Um, so let's see what we are. So we can actually focus again on the endpoints for which range trees are interesting. We may also have segments that actually lie on the boundary, or actually they intersect the boundary. So in some sense, focusing on the endpoints only may make that we are going to lose segments. So the approach of last time that made the connection with range trees, and also earlier we made the connection with range trees, so that might not really solve our problem. So all of a sudden we would kind of see segments disappearing from view. Um, So if we consider queries that are vertical query segments, so what we have given is an interval, and then we have one coordinate. So it's like the stabbing queries from before. So if we think about, again, a relaxation of the problem, instead of looking at the entire green window here, we look at a vertical query. And then we see that all these segments are actually projected down to intervals. So similar um, approach that we took at the beginning of this problem. But we're going to look at intervals again, but we're going to look at them differently. So you see that one vertical line segment projects to an interval that contains only one point. Okay, so this is a vertical query segment. In order to search efficiently, we like to report in logarithmic time, logarithmic in the size of the input. So coming back to our interval trees, so we have all the intervals in our map and we select the medium. So does the intersection then with that median that actually imply that you are in the window? Um, Obviously not for this case here. If we would solve this with the median, we would actually exclude a lot of segments. An interval tree actually is useful, but we can do better. Here is the locus approach that is suggested by the textbook. So what's the paradigm for developing data structures? Well, if we look at again an entire query window, not just a vertical query, we will observe that if your windows are very nearby, we might get the same answer. So actually, if we want to, and actually what we're trying to do is we want to have extra data structures. If we want to pre-process the data, then one way to do this would be to partition the parameter space, and the parameter space is here four-dimensional, into regions, such that if you have the partition, so that if you are in the same region, you have the same answer. So what we will do is we will apply this approach. It's kind of an idea by chopping up, actually segmenting the line segments. So that will give us an alternative to interval trees. And that will allow us to efficiently deal with vertical segment queries. Okay, so here is the idea. So if we are given a set of intervals, then we can again focus on the endpoints. And how do we get these distinct intervals? Well, we projected all our line segments on these intervals. So we have a number of distinct points, and we're going to sort those distinct points and define the elementary intervals. So in some sense, it's a partition of the entire line, so going from minus infinity to plus infinity, not included. So there is this round brackets, which means it's an open interval. The closed intervals are these distinct points, so the endpoints that we have sorted. So in some sense, you could say that one given interval actually now spans several elementary intervals. Another way to seeing this is that our original line segments, they have been chopped up into different pieces. So these are the elementary intervals. What does that do for us? Well, we can start to organize these elementary intervals so that we get a binary search tree that will allow to give us queries. So in going from this slide to that slide, you can kind of see that some intervals will be more important than other ones. And that means that the intervals that are spanning many elementary intervals, they actually should be higher up in the search tree, because if things are larger, we want to find it earlier. Things are small, you can accept that you will need to go a little bit deeper into your binary search tree. So this is the basis. So if you can find the elementary interval that contains your query point, so we have a vertical query point, then actually we can find all the intervals that that point contains. So you can see that we can kind of find intervals in that way, execute a query based on this first partitioning of the entire horizontal line in elementary intervals. Okay, where does the tree now come from? Well, we can group the intervals. So we can start to make, so we have the elementary, we have the points, but then the leaves actually contain, um, I'm sorry, so we have a binary search tree where actually we have leaves that are points. So points are actually also intervals. That was what confusing me a little bit. So if you look to the left here, we have the interval minus infinity time to P1. So that's the left branch here. Then we have P1 itself. So that's the second interval. The third interval is the interval P1, P2. And then the fourth interval is the interval P2 itself. So if we have a line segment, actually we do have an interval P1, P2, then actually this will correspond to the points P1 and P2, will actually contain these three leaves here. So intervals, so if we're going to store now the intervals at the nodes. And the leaves, so the nodes actually define a subtree, and the leaves of the subtree will contain all the elementary intervals that are contained in the input interval. So if you can locate one of the elementary interval, then actually all the intervals that contain this leaf and the subtree actually should be considered. Um, that's another way how you can do your search from bottom up. So by the way, the trees that we are seeing here are like the natural trees, not like the trees in computer science, which grow from top to bottom. Here actually we grow them actually from the leaves up to the root. So we still are growing our trees starting from the elementary intervals down to the root. It's still an unnatural way of working, but the result we can display it as a natural tree. So we have our given intervals, the elementary intervals at the leaves of a tree, and then we still have to define what are the intermediate nodes. So that is what we are going to, that's the point of this slide here. So we have this, so let me first say the principle. So it's a little bit like the priority search tree or the heap that we had in the previous lecture. Things that are more important, they are closer to the root. So the intervals, you're going to store them in this tree that has as the leaves the elementary intervals. We're going to store those intervals at the nodes, but as close as the root as possible. So we want to um, so we want to store every interval on we will show that we will only show it at most, store it at most twice. So we do not want to store one input interval everywhere it occurs on the path to an elementary interval. We want to store it as high as possible. So here on the example, the highest that we can store it would be at this location here because it contains the interval P3, P4, also P2 essentially. But not strictly speaking, this P1 minus infinity. So we can't store it any higher than where it is already here. Or in some sense higher in the tree, I'm still thinking computer science, towards the root. If you see this as a natural tree, you could see the depth, how deep you should go. Okay, so this is one example. The purpose of this exercise is that you start labeling all the line segments and start placing all the input segments on the nodes of the tree. Note that one node can contain many intervals. So this is an important exercise to verify also that you will store any segment once or at most twice in this um, tree. In some sense, if you have as close to the root as possible, it should be only at most once essentially. But you can try to ask yourself now, in which situations do we store an interval multiple times? That's an additional question to ponder. Okay, in some sense, this is already um, the essence of the lecture, or a very important. We have not yet gotten through any formal definition, but I hope that at this point you get the idea of a segment tree. Okay, it's time to look for some more examples. So we are using Seagull in this course, so the computational geometry algorithms library. So in this, so there is a package overview. If you look at the package overview on spatial searching and sorting, we have seen already in an earlier chapter range queries, rectangular range queries. We started the chapter on interval or stabbing queries, and for this lecture we are in the segment trees. You see they are kind of grouped together with the range trees, and this is to perform window queries. Okay, if we look to the user manual, so we can skip the section on range trees. So range trees are multi-level data structures, and we will again see that in order to do vertical query segments, we will also actually work with associated data structure. So in segment trees, so here you see the documentation. Again, this is another way to view the material. You can see the terminology. And then I will go through this example to illustrate a window query. So here you see, if you look at the output, you see a window query that is executed on intervals. Okay, so the code is relatively straightforward. So here is the code again. So just to indicate that we are working with a segment tree. Um, the examples of Seagull are stored in a separate folder. So if you are working on a Windows subsystem for Linux or on any Ubuntu installation, the package manager should install Seagull for you. Uh, in the examples, you can look for range segment trees, and there you find the corresponding code on the package overview the documentation that we just browsed through. So the exercise that corresponds to this, do we actually, when we construct these segment trees for sufficiently large intervals here or large point sets, do you actually observe the n log n? And you may have to figure out a sufficiently large data set to actually see this. Okay, I have prepared this. So, and I have prepared makefile. So the makefile defines the compilation instruction, and here is how I'll now run this. So there is the window query that is executed. And so you can see the code. So here is the code. And then there is the window query that is displaying then the output. So this is for a segment tree that is constructed from the input list, so statically constructed from the beginning and the end with the intervals, so only 4 intervals if I read this correctly. So the purpose of this exercise is to see that you can do this for larger values for n. So then the script goes, the code goes further with an enclosing query. Okay, so this is just to get started. So an important activity that is recommended that corresponds to this lecture is to browse through the documentation and the corresponding test programs. Okay, so this is the first half of this lecture. So let me now continue to the more formal definition and the properties of the data structure. Again, the main question is, can we perform these windowing queries? Can we do them efficiently with a segment tree? Okay, here is the definition of a segment tree. We start by ordering the endpoints of our input intervals, so sort them, and then define the elementary intervals. So in some sense, this is a partition of the entire real line, starting from -infinity to the smallest endpoint. The endpoints themselves are closed intervals. Then what is between the endpoints are the open intervals. So we use these leaves, we use these elementary intervals to construct a balanced binary search tree. So the leaves are actually ordered from left to right. That's the balanced binary search tree. Then we have the internal nodes. So every internal node is actually the union of the elementary intervals. So the interval of the node, so you can store an interval by the left point and the right point. So the interval is stored. And then also what is stored is the set of intervals. So we have all the intervals that actually are containing the left and the right bound of the uh, points at the leaves. Now, so then we define the canonical subset at the node contains all the intervals. So the interval at the node is actually contained. And the interval of the parent, so that's the node that is still higher, actually is not contained. So this is important. So we do not want to store the input intervals too many times. So we had the principle of a segment tree that we store each input segment as high as possible, as close to the root as possible. Here now we give a formal recipe. I said every node stores an interval that contains the leaf, but actually if we have um, an interval that contains two leaves but also contains the leaves under the parent, we're going to store that interval then at the parent. So each time we try to see, we are taking an interval, we are starting at one of the leaves that it contains, and then we move up towards the parents. Until we get stuck, we cannot move any farther because the parent actually then contains leaves that are not contained in our interval. Um, so exercise 1, we try to do this on an example. Here actually we have now a definition which is at the same time kind of constructive. So if you get stuck with exercise 1, you can do exercise 3. So doing exercise 1 and exercise 3 is kind of the same thing. So that's kind of the point here. So we have the elementary, we have in this definition in red, so this is an entire definition environment. Originally, I had it all on one slide, but I decided then to split it. So we have the elementary intervals that are at the leaves. And then we have the, at each node, we have this interval xx prime, and then also the canonical subset um, that satisfies these properties here. Okay, we are concerned to store not too much, so we definitely do not want a quadratic storage, so we can do with an n log n. So in some sense, again, it depends on the application. We have n segments. Can we afford to multiply the size of our data set by the logarithm of it? So if you have essentially 1,000,000 elements, can you afford to store 20 million? So that's actually the question in practice here. If you can't afford this, then segment trees are not for you. So interval trees are cheaper. But then you have to rely on stabbing queries, and there you may have sometimes too many. So you may need then an additional filter. Okay, let's try to prove this lemma so that the storage is proportional to n log n. So what do we have? We have the n input intervals. So we have at most 2n endpoints if they're all disjoint. Um, so we have this partition. So that's where the 2n comes from. So then we have everything that is in between. So this is 2n minus 1. And then we have the outside intervals. So at the leaves, so this is actually the worst case if everything is distinct. Um, so at the worst case, we have 4n plus 1. So we have a linear number of leaves. So the tree is a balanced binary search tree. We can construct it that way. Everything is static. But now we have to store still the input intervals. So how many times does every interval occur? Um, Okay, so we will insert in that balanced binary search tree the uh, input intervals. Okay, so it's important to have this property again. So the definition of the canonical subset. So at a node, the interval actually is contained in that, but the parent is not contained. So this assures that any given interval is stored at most twice. Again, the question is why not once? That was the question that was raised with exercise 1. Find an example, and perhaps solving exercise 1 will actually point this out, that you could store any given interval twice. But the point is, and that's actually the point of the proof now, this is where the point comes in. Assume that you would store it 3 times. Then actually we would violate the principle, the definition of a canonical subset. So assume that at the same depth we have these 3 nodes, and again we have the leaves that are ordered from left to right. So somehow we have this middle node V2 that is sitting there. So it actually spans the whole interval. But this middle node lies actually between the two. Actually, that interval actually is contained actually so the parent is actually also contained there. So we actually are violating at that node V2 the assumption. And I think that this counterexample, so it's an abstract one, that if you picture it, so if you read this again carefully in words, that you can make a drawing where you have the 2 nodes V1 and V3 that actually store 1 input interval. But the intermediate and the parent actually are not storing it. So I think you can construct from this proof of the lemma, you can draw an example where you have 1 interval that's stored twice, but it can never be stored 3 times. So as mathematicians, we like proofs. Some proofs are very important because they also shed extra light on the constructions of the data structures. Okay, how do we query a segment tree? So this is a vertical query. So we have a query point, and here we will report all the intervals that are containing that query point. So we will report all the intervals in the canonical set. So we actually go top down. So all the intervals that are there, and that's actually the largest interval that we can place there. So we go thus down towards the leaf. So we have an XX prime interval at every node. If we are to leave, we are actually done. So it's a recursive algorithm. So we can very quickly check if it's in that interval XX prime. If it's in the left, we go to the left. If it's in the right, we go to the right. So if it's not a leaf, then we are actually um, we have two children, and we can check the left child and the right child. So, and at each node, we report all the intervals that are stored there. Okay, so it's an output sensitive algorithm. We are having to go all the way to the leaves. And the depth, it's a balanced search tree. That's how it was constructed. So the depth is logarithmic in the total number of intervals. So the leaves, we proven this, it's at most 4n plus or minus 1. So the depth is logarithmic. At each node, we report a number of intervals. So that's the time that we spent there. We also do some testing. So the sums of all the reported intervals equals this k, which is the output size. So we have an output sensitive algorithm. Okay, so how do we construct now a segment tree? So um, when we construct a segment tree, we're going to insert an interval. So that interval is part of our input. So we check whether the interval at the node is contained in the input interval, then we store it there. Otherwise, we will store it at the left, or we will store it at the right. Um, Okay, so the point is here, is there no test on the leaf? Well, actually, every node contains this interval. So now it's a little bit strange with the notation. The interval that was stored that contained kind of the span of the elementary intervals, I also called this xx prime at the time. Now here xx prime is the input interval. So at every node we have another interval that is there. Shouldn't be referred to as xx prime. Um, so the point is, do we ever, so if the else happens, you actually are not at the leaf. So in some sense, that is kind of the um, correctness that needs to be handled here. Um, so if you would somehow bump up to a point that you can't store your interval anymore because the else is failing, that would actually mean that you have not constructed your tree correctly. So you somehow left out an endpoint. So that's important. So the correctness of the algorithm depends on the correctness of the construction of the elementary intervals. If that was not done right, then yes, indeed, this algorithm will not be working. So that's the point that I want to make here. Okay, the costs. Well, the depth is logarithmic, so we will visit at most logarithmic of n nodes. So then a segment tree, um, we have to sort, so we have the n log n time of the construction. The storage, as we have proven, is also n log n, and the query time is output sensitive. So that's the performance of a segment tree. Okay, so did we now solve the original problem with the vertical query segments? Well, what the segment trees essentially do, they allow to locate the vertical segments. So every segment actually spans a slab. So here is a very simplistic picture. I was originally thinking of having the S1 all the way on top to suggest kind of the tree, but it shouldn't be that way. So that would have been too oversimplifying. So in our segment tree at the root node here, we have our segment S1, and then at the children, we have the other intervals that are stored. So the canonical set is a set. So for efficient lookup, we would actually order the segments in another tree vertically, so that we can efficiently decide which segments to report. Okay, so that's the associated data structure that will be stored at each node. So we have now a multi-level data structure. So the storage is actually not increased. So we're going to sort one more time, but also that does not increase the storage time, the overall time. And in some sense, I'm summarizing topics, but in previous discussions on orthogonal range queries, we handled multi-level data structures there as well. So we can do the sorting on the endpoints or on the line segments. We can do this also as a pre-processing step. So it's not that we sort again at every node. So that's important here. We do not essentially store anything more. That's also important to realize. Now, what does gets elevated is actually the query time. So we have a logarithmic search in the segments, and then we have in each slab we have another logarithmic search. So this is where we have the square of the logarithm in the search time. Okay, I hope that the main ideas were becoming clear in this lecture. So the locus approach led to segment trees. That's an approach to construct data structures. So a partitioning of the parameter space so that same or similar queries would give you the same results. That led to the segment trees, in some sense segments of line segments, but also segmentation of the input. The main result of the last slide is here written down in one sentence. N log n time for the sorting, n log n time also for the associated data structures. There is a remark that says that the log square can be improved. I leave it up to the notes in the textbooks. Now the exercises are kind of essential for a further understanding, especially exercises 1 and 3. We still need to verify because they are kind of essential in the storage costs. The purpose of these lectures is that you become familiar with reading the textbook. So I'm following the textbook, but in some sense, I'm trying to give an introduction to the textbook, not a replacement of the textbook. My hope is that reading the textbook will become clearer, and perhaps it's also necessary, as I often leave out details or introductory reasonings. The textbook may also contain pictures, more pictures than what I can give. Then referring again to Seagull. Seagull is a complicated but very comprehensive algorithms library, and I hope that by now one gets a little bit more familiar with how that software is helping us understanding computational geometry. So this lecture is a milestone. We are closing chapter 10. We have the preparation for the midterm in the next lecture. After our second midterm, we will look into convex hulls in tree space. So that's the main topic in chapter 11 that we try to cover carefully because also of its importance to computational geometry. The hope is that if you understand how things work in 3 dimensions, one can go to higher dimensions if necessary. So I hope this was interesting, and I stop the pre-recording here.